Good. Maybe we can slowly start. It's already too fast, and we have already quite a number of people in the room. So my name is Michał Pilipczuk. I'll be chairing this seminar. So let me start with some logistical stuff before introducing our speaker. So first of all, we will have 3 sessions, 50 minutes each. I guess you have seen the plan. The meeting, the seminar will be recorded and it will be then made public. So regarding the questions, you can either just interrupt and ask your question, but note that if you do it, then you will be recorded and your voice will be therefore made public. An alternative for raising a question is you can always write a question in the chat, and then I will read the question aloud. Good. I guess that this is for the logistical stuff, so we may slowly proceed to starting. So it's my great pleasure to introduce the speaker for today at Friday afternoon seminar, Ryan Williams. I guess that Ryan doesn't really need introduction in the area of computer science.
I watched it from the beginning, or I don't watch it at all.
I'm sorry. Ryan did his PhD at Carnegie Mellon in 2007, and since then he has been a professor at Stanford and now MIT. And he works in computational complexity and is one of the few people in the world who dares to attack really fundamental questions in complexity theory, and in particular in circuit complexity, and with some spectacular successes. So not many of us are able to claim fundamental results on lower bounds for computational problems, and I guess that this is what we will be hearing about today. So without further delay, Ryan, the floor is yours.
Thanks a lot for the very nice introduction. Maybe send me a private message if when my time is up, because I don't know. I mean, I have clocks sitting around, but it's not clear I will be looking at them if I get really into thinking about complexity theory stuff. Yeah, thanks everybody for coming. I'm happy to talk about this. I haven't given a seminar of this length virtually before, so we'll see how that goes. Yeah, we'll see. So as promised, this talk is about barriers and pathways to complexity lower bounds. And we're going to be looking at 2 questions at a high level. What could a proof of P different from MP look like? Or what could a proof of kind of any major open complexity separation look like? I mean, P different from MP is just a proxy, P different from P space, things like this. I mean, we don't quite know. We have an idea, and that's why it's only the last 1/3 of this lecture. What will it not look like? We have a much better idea about, and that's the first 2/3. Okay, and so what will it not look like? This is discussing the topic of barriers, and generally speaking, this the topic of barriers is talking about weaknesses in techniques for proving lower bounds, and there are various barriers that have been proposed. Many of them talk about like kind of specific approaches will not work. What we're going to be looking at are general, some of the most well-known and most general barriers. The first is the oldest, relativization, but also has been recently upgraded to algebraization as well. This is initiated by Baker, Gill, and Solovay in the 70s. So we'll look at this oracle model for algorithms. So it's augmenting the algorithmic model with a special operation. We'll see that there are oracles so that P is equal to MP, oracles such that they are different. And this is very problematic for a lot of techniques in complexity theory, because they often work if you stick oracles in your model of computation. So lots of theorems in computability and complexity still hold in the presence of arbitrary oracles. So these two A and B are telling us that P versus NP is not going to be resolved by a technique which goes through with arbitrary oracles. So then we'll talk about non-relativizing lower bounds. Lower bounds, so in other words, impossibility results for which there is an oracle so that the lower bound is false. So these things are separations we were able to prove, or results we were able to prove. Sometimes they're upper bounds, sometimes they're algorithms, where there actually are oracles contradicting. And then we'll talk about the algebraization barrier, which gives a new barrier for some of these non-relativizing lower bounds and techniques that have been shown. And then we'll talk at the end of this discussion about relativization, algebraization, about some pathway that some ways which there is no barrier known, which but they're non-relativizing. Okay. The second part we'll be talking about something that's often called natural proofs, but because I'm talking to people in logic, I don't want to say natural proofs too much. I want to call it the Rasburov-Rudich barrier. Okay, this is not something proof theoretic really. It's some algorithmic property that holds for many weak circuit lower bounds. And the point of this algorithmic property is that it's a bit too strong. If similar properties held for stronger circuit classes, this algorithmic property would actually break cryptography, like all possible one-way functions and things like this. So in a sense, like this natural proofs or Rasburov-Rudich barrier is a self-defeating thing. It's like you're doing too much. You're doing so much that if you manage to prove a lower bound using like that has this algorithm in it, that in fact you've broken cryptography, so you don't have like any lower bounds like that are stronger. You don't have these average case lower bounds. So the relativization barrier is somewhat similar, I guess. Like sometimes if a theorem relativizes, if it works with oracles stuck in, then that actually is very good. It means you get lots of other theorems for free because the same argument works in a much more general setting. But that somehow that's just too strong, or sorry, maybe too general to separate or distinguish P and NP. So those will be the two barriers we'll look at largely, and then we'll talk at the end about a pathway. So these so-called constructive lower bounds. This is joint work with Lijia Chen, Sajin, Rahul Santanam that appeared in Fox. So roughly speaking here, I don't want to give away too much, but the idea is that for these major separation problems like P versus NP, P not equal P space, we can prove that if the lower bound holds at all, then there is somehow an algorithm, another kind of algorithm hiding in it. So this is a bit weird because if we say, like, say, P different from NP, we're saying some negative statement about polynomial time algorithms. But if that lower bound holds, there exists other kinds of algorithms, and these are these are basically algorithms which can print bad inputs for a function. So if I prove a function is not in some class, there is an algorithm which will print a bad input that shows you any given weak algorithm does not compute this function f, this hard function. This is some kind of constructive method for witnessing the lower bound. So an interesting aspect of this is that we can show that essentially all open separation problems regarding polynomial time require a constructive separation. In other words, this algorithm, this polynomial time algorithm for like finding bad inputs for a weak algorithm just exists. It just must exist if the lower bound holds at all. So that's point one. And the second point is that making known lower bounds that we know to hold, making them constructive would require resolving other major lower bound problems. So the upshot of this is that constructivity, whatever this thing is a property we want of lower bounds. So it's like the opposite of a barrier, which is something you do not want. You do not want to relativize or naturalize, have a Rasburov-Rudich barrier. This is something you really want to achieve. It's harder to achieve but it's necessary for resolving major problems. Okay, so that's a quick overview of what the whole thing will be like. But yeah, please ask questions in the chat once we start getting into this technical stuff. Okay, all right, so this, for some reason, the iPad is still moving after my hands went away. All right, so now let's start talking about the relativization barrier. All right, you can see my laser pointer okay here? Yeah. Can you? You
Actually,
can't?
I do not see the laser pointer.
Uh-oh. Yeah, okay, what if I highlight? Can you see that? You
Where
can't see
did
the
you highlight? Oh, yes, but it
Okay.
is super slow. I think we have, at least I do have a large lag in
I
whatever
see.
you're doing on the iPad. Oh, now I see the pointer.
Okay, now you see the, all right, all right. All right, I will, okay, I'll try to point slowly. I don't know, or I don't know. Okay, so to explain the relativization barrier, I'll just keep the laser pointer on here for now. I need to remind you of what like an oracle Turing machine is. So we imagine just a Turing machine usually has some input tape that's read-only, has some read-write storage, and a Turing machine with an oracle has a special oracle tape. And we think of this oracle, actually, we want it to be like a sort of a function over arbitrary strings, so arbitrary length bit strings. And the idea is we get to write whatever we want on the oracle tape. We enter some query state and we just can ask yes or no questions. So like, so yes would be that the oracle outputs 1, and no would be the oracle outputs 0. Okay, just think of this as some special operation that we get to add, and we write this notation m to the a to say that the machine, this is a normal Turing machine, but it gets to ask unit time questions to oracle a. So like in unit time, it can just get back an answer. It might take some time to construct this query, right? And so this is just a description of that. Now, another way of thinking about this is if you like thinking of pseudocode instead, you're just adding this extra if-then operation to your pseudocode, that you're just checking if this oracle on Z outputs 1, then do something else, do something else. Okay, you're just adding this extra operation. Now, the thing is, so A can be arbitrary, okay? And yet many theorems still hold when oracles are added, okay? So just to give some examples, like the universal simulation theorem, saying that we have a universal Turing machine. There's a use that for all algorithms n, input x and positive integers, if I give it the code of the algorithm, the x, and the string of t1s, I can check whether it accepts within t steps. Okay, this is just a universal simulator. There's an oracle version. If I stick in oracles everywhere here, if I give my universal Turing machine the same oracle, my algorithms have that same oracle, the simulation can be carried out. Okay, and when we say this, we say that the theorem, this universal simulation theorem, relativizes. It holds relative to every oracle. This is very powerful. Okay, so you can think of it as generalizing a theorem to hold for uncountably many computational models, right? Because there's uncountably many choices for the possible oracle. So you kind of just get this for free when you prove a relativizing statement. And here's just some more theorems like this. So most theorems relativize. Like if I have the halting problem with an oracle, I can show that no Turing machine with oracle A can decide the halting problem with that oracle. There's a way to have an oracle version of the 3-sat problem, and it's MP to that oracle complete. You can have problems in order T of n time with oracle A, and the time hierarchy theorem holds. You can find problems solvable in like quadratic time that cannot be solved in linear time with an oracle for A. Like all the usual inclusions, like P containing NP, hold with oracles A. There's so many different things. Okay, so a lot of most things that you would do, especially in a basic complexity course, would relativize. You can stick in oracles into the model, and the theorem will still hold. Okay, and the big problem with this is that there is oracles relative to which P equals NP, and there are oracles relative to which P is different from NP. Okay, so So already the oracle making them equal says to prove P different from NP, we're going to need proof techniques that will yield non-relativizing theorems. So somehow you cannot be doing like a step-by-step black box-ish simulation of the machine, the arbitrary machine. You can't just simulate the thing and then do the opposite. You've got to be more clever than that. Like there has to be some way in which you're like if I stuck in an arbitrary like operation, an arbitrary subroutine you can call, the argument will break. Like this, and it's kind of funny. Like it's difficult to come to think of something where that happens. When you look at circuit complexity, it makes it easier because like if I'm looking at a circuit made up of like and or and not gates, you can imagine some inductive argument that has three cases. Like if I see a not gate here, I do something. If I see an or gate here, I do something. An and gate here, I do something else, and I have no room for an oracle in those arguments. So this is kind of why people were looking at circuit complexity after relativization barrier. So anyway, let me discuss why there is an oracle making P equal NP. The basic idea is you make an oracle so powerful that the difference between non-deterministic polynomial and polynomial disappears. Okay, so we define like a problem x except this problem takes an m and x and the string of t zeros, and this is in the language if and only if m accepts x and at most 2 to the t steps. Okay, and the length of x is at most t, the length of m is at most t. So just by definition, this problem is an exponential time. Like it takes me exponential time in the input length to do this simulation. Okay. Now recall that the class exp is the union over all k of time 2 to the end of the k. So this is exponential of a polynomial. So then the theorem is that this exp actually just equals P with an oracle for exp accept and MP with an oracle for exp accept. Okay, so like everything just becomes the same, it just becomes exponential time. Okay, and the argument is pretty easy. So sequence of inclusion. So first, exp is in P to the exp accept actually with just one query to oracle. So let's say I give you some exponential time algorithm. I just define my polynomial time algorithm to take an input, okay, create some instance with, this should be, I guess, this should be A, okay, with the algorithm A, and the input X, and it just pads it with polynomially many zeros. And it just checks where this thing is an X accept, right? But whenever I stick in this many zeros, that's 2 to the length of X to the K running time. So this thing is exactly just simulating A and 2 to the length of its input to the K running time. All right. So it's just one query to this exponential time problem does it. Now we already said that P with an oracle is always containing NP with an oracle. So this part is immediate. Now why does NP with X accept in X? Well, the idea is that an NP machine can only like in any particular path, it only runs for polynomial time, any particular computation path it might take. And so the queries it can ask are only of polynomial length. And on any particular path, it only asks polynomially many queries. So given some non-deterministic machine with this X accept oracle that runs in n to the k time, we define an exponential time machine that just tries all the 2 to the polynomial paths, computation paths, all the possible sequences of transitions it could take, all right, that would lead to an accept state. And they just simulate each query it makes to X accept. And that will also take 2 to the order n of the k time because the length of the queries is only order n of the k, right? If it runs in n of the k time, it can't make a query longer than that. And it can't make more than n of the k queries. Okay, so there's only 2 to the order n of the k queries at most. Each one can be simulated in 2 to the order n of the k paths. We multiply all these together. This is exponential time, right? And finally we just accept if and only if some path leads to an accept state. Okay, so everything could just be simulated in exponential time, and we're done. Okay, so this oracle is actually pretty easy to see. But are there any questions? Okay, so
nothing on chat, so we can continue, I guess.
Yeah, I mean, in general, you could actually take, a p-space complete problem, use something that's hard enough, and it will collapse P and NP, right? If it's your oracle. Now, it's more complicated to show. Can you still see my laser pointer? Okay, good. Because I last time it went away when I did the scrolling thing. Okay, so there is an oracle that makes P and NP different, and so as a conclusion, relativizing methods just can't resolve it either way. And the nice thing about this theorem, this oracle, is that it actually formalizes our intuitive idea of the needle in the haystack nature of P versus NP. So like we're going to make up a language that's just obviously an NP to the oracle, but it basically involves guessing a needle in a haystack, and we'll make it so that we'll design the oracle to like be so devious and so clever, it is actually hiding needles from every polynomial time algorithm that tries to query for a needle in the haystack. Okay, so we define a language L sub B, okay, which is going to contain the string of n1s if and only if there is some string of length n for which this oracle reports 1. Okay, all right, so again, we think of this as just some function from arbitrary length bit strings to 0, 1. And so for every oracle B, this L sub B is an NP to the B. Okay, if I give you the string of n1s, you just guess the needle. Okay, this X is like some needle in a haystack. And right, if the oracle reports 1, we accept, else we reject. So clearly we can just guess the answer and check it with the oracle. All right, an NP to the B, no problem. All right, so now we'll define B so that L sub B is not NP to the B. Okay, and the key fact is that a polynomial time algorithm can only query poly n strings on 1 to the n. Okay, that's the key fact. So it can only query about polynomially many places. If it could query about 2 to the n strings, all 2 to the n strings, this argument is not going to work. Okay, so it's using the fact that the thing can only query polynomially many strings, like whether or not they're in the oracle. Right. So the way it works, at a high level, you take a list, like indexed by like some I, so n sub I, of all Oracle Turing machines running in polynomial time. Okay, so it could be the ith Turing machine set to run for n to the I plus I steps, something like this. So just take some enumeration of all Oracle Turing machines. And we don't have to really specify the oracle. You could just have this like pseudocode that enters a query state, and then based on whether it says yes or no, it does something. Like I don't have to tell you what the oracle is. I can just take a list of all the Turing machines that could have an oracle plugged into them. Okay, all right. So I'll start with this list, and what I'm going to do is I'll make an oracle that's constructed in stages. And in the ith stage, we're going to kill the ith oracle Turing machine here. Okay. We will kill m sub I with a B oracle. Okay, initially, this oracle will just output 0 on everything, just zeroed out everywhere, right? So the haystacks are all empty, okay, at the beginning, and then we're going to stick needles in particular places. We'll set some to be 1 to fool whatever our algorithm is doing, the ith algorithm at the time, okay? So if I is 1, then we set, let's say, n sub I to be 1, or just some sufficiently large constant. Otherwise, n sub I needs to be larger than the maximum length of all queries to be in previous stages. So in all places we set needles in previous stages, okay? And we also need that there's enough strings so that like there's more possible strings of length n sub I than there are queries that we could make to those strings. So like our ith algorithm will run into the I plus I steps. Right. So there's more needles than what we can query, and this new input length n sub I is much longer than anything we looked at before. So this is how we can make a consistent oracle that will continue to fool the ith machine for all I. Okay. So the next thing we do is we just simulate the ith machine with this oracle B on the string of n sub I ones. Okay, but we have to be careful, right? We need to be consistent with all the previous stages, whatever it is we said, in the previous stages about like a query or a needle that we stuck in, we have to give the right answer, okay? But for all new y that were not asked before or that we did not stick a needle in, we're going to answer 0. Okay, so I mean, because well, it's initially 0, so we just answer 0 to all of those. Okay. All right. Now, if this machine decides to reject, okay, then we got to stick a needle in there to fool it, right? It said there was no needle of length n sub I, right? Recall, right? When on n sub I ones, we got to ask whether there's a needle in the haystack of size n sub I bit strings. Okay, so then we pick some string that was not queried, and we set the oracle to output 1 on it, right? So we were sticking in a needle. If the thing accepts, okay, it claims there is a needle, then we do nothing, okay? But by answering 0 to everything, we've ensured that the haystack remains empty. So in fact, there is no needle, even though it said accept, okay? And so the claim then is that for all I, this machine will accept on n sub I ones if and only if actually n sub I is not an L sub B. So we've managed to find an input which is bad for every single polynomial time machine with Oracle B. All right. And you can extend this to exponential time bounds to show that like this L sub B is in fact like appropriately defined as not even in little o of 2 to the n time with this Oracle B, because the key property really is that, let me see, the key property really is that you're picking something not queried, right? So as long as there's kind of enough strings more than the running time of your machine, right? So just enough, so more than the number of queries you might make, there's always some string you did not query. As long as you can ensure that, then the argument can be made to work by just making it sub I super large each time. Okay. Okay so far. All right. Right. So for practically every pair C and D of complexity classes where the C versus D problem is open, there are oracles making them equal. And here's just some of the most embarrassing examples. So there is an oracle A so that exponential time with an oracle to NP that has an oracle to A is equal to BVP to the A. So this is randomized polynomial time. Okay, so there are oracles for which exponential time with an NP oracle collapses all the way down to randomized polynomial time. Okay, now this is about as much of a collapse as you could expect, because like already just by the fact that the time hierarchy theorem and things like this relativize, x to the NP with the oracle for A is different from p to the NP with the oracle for A. And in exp, non-deterministic exponential time with an oracle for A is different from NP with the oracle for A. Okay, and that's true for all A. Those, because these hierarchies, these time hierarchy theorems, they do relativize. So there are these oracles which are called like massive collapses. And you can even collapse like non-deterministic exponential time to p to the NP. Okay, and like wild thing about this is that, like, one side can query exponentially longer strings than the other side, yet you can set up the oracle so that in say p to the NP, it can do some kind of binary search through this oracle and figure out whether the non-deterministic exponential time machine accepts it or not. So these are due to Heller and Berman, Finner, Fortnau, and Tourneville. So, but yeah, so this basically shows that, like, even these embarrassing separation problems are going to need something that is non-relativizing, like these long-standing problems about the power of randomness and the power of even p to the NP. It's pretty wild, like that things can collapse so far. Okay, so that suggests, okay, so how do we get non-relativizing methods for lower bounds? Well, so there's, I guess, generally speaking, three classes of methods, I would say. The first is algebra methods, okay? And at a really high level, what do? You construe the computation in some form or another as a low degree multivariate polynomial, okay? Like, so it's some polynomial in many variables. Let's say it's a problem on it takes like Boolean inputs of length n. Okay, so this is a polynomial in n variables, and it could have some low degree in so each variable, let's say, has low individual degree. The used Schwarzschild and like and randomness and low degree polynomials to prove some like kind of mind blowing theorems. So like the PCP theorem says that like NP verifiers, so non-intrinsic polynomial time verifiers, can be replaced by randomized verifiers that just make constantly many probes into a polynomial length proof. So like they're like super lazy, right? Just using randomness, they can just probe like a few places in the proof and not be fooled with high probability. Okay, and this crucially uses algebraic methods in this way. And there's nx equals MIP showing that non-intrinsic exponential time can be captured by having interactive provers, multiple interactive provers that a verifier can consult and ask different questions to about like its input. And if it's interacting with just one prover, then this turns out to be another characterization of p-space. Okay, so these are just interactive proof systems, but it's crucial, very crucial that the verifiers here can toss coins. They can come up with sort of random challenges for the prover to satisfy. Okay, and there are lower bounds that are proved by algebra methods. Here's one. So for all constants k, there are problems decidable with Merlin-Arthur proof systems. These are basically like one round interactive proofs. It's basically randomized NP. Like Merlin is like like something sending you a non-deterministic thing, and Arthur tosses coins for some reason. This is NP with randomized verifiers. So these do not have end of the k size Boolean circuit families, and this is a non-uniform complexity result. It's striking. So this is a version, this was first proved by Santanam in 2009, is striking because we would really love to prove something like this for NP. We would love to prove some nonlinear circuit lower bounds on NP, but we can prove it for Merlin-Arthur things when you stick in randomness. And the bottom line is because of these algebraic methods you can use. Okay, I want to say none of these theorems relativize. So there are oracles for which they're all false in the way they're stated. Okay, but they're nevertheless also subject to a new barrier, well, relatively new compared to relativization, which I'll talk about in a moment. This algebraization barrier. Okay, so another method for non-relativizing lower bounds is that of for lack of better terminology, call them probabilistic type methods. And these typically lie in non-uniform circuit complexity. So roughly speaking, these are lower bounds on circuits via some method, call it M. And this method has the following property. Given the truth table of a uniform random Boolean function, the method will declare the truth table to be hard with high probability. And this is natural. I mean, if you, right, like almost any kind of succinct representation you might think of for succinctly representing a Boolean function, a random one cannot satisfy it by a counting argument. Okay, so it makes sense that if something is actually good at telling hard functions from easy functions, it will work on random ones. Okay. On the other hand, if T has some efficient circuit, or if there's some efficient way to compute the thing, all right, then M declares it easy. All right. And finally, M can be implemented efficiently on any truth table. So in other words, there is some way to get an algorithm which, given the truth table as input, will do this hard and easy declaration. Okay, it seems like something reasonable to expect from a lower bound, and many of these sort of probabilistic methods end up showing this kind of thing, that so random functions are declared hard easy is declared easy, and in fact, there is an efficient way to tell the difference. Okay, but this is exactly the Rasburov-Rudich barrier, actually. So M declares T hard. So we think of M as like an algorithm that takes in the truth table T, and let's say it has two possible outputs, hard and easy. That's what I mean. Does it make sense? So think of M as like some algorithm that takes in T as input and has two possible outputs, hard or easy. Okay, so so it either outputs hard or outputs easy. Because yeah, we think of it as being implemented efficiently on any T. Is it okay?
So maybe more basic question: what is a truth table?
Oh, so we just think of it as a string of length to the n. So to the n bit string that's defining a function from n bits to a bit.
Mm-hmm.
Yeah, so it's taking this 2 to the n length bit string, and it's running in, let's say, often they run in polynomial in 2 to the n time, and then they make this declaration, easy or hard.
Okay, either a hard function or easy function.
Yeah, and all we require about this is that it declares most functions are declared hard. Random functions are declared hard with high probability, and the easy ones are declared easy. And that's it.
Okay.
And this is already the setup of the Rasburov-Rudich barrier, and it frequently arises when you have some probabilistic method for lower bound. And yeah, we will see some more examples later of this in the second part. But yeah. So this, I mean, this was what people began to turn to after the relativization barrier because of, I mean, roughly speaking, because of the reasons I was describing. If you've got a circuit and you've got like, or, you got and, you got or, you got not gates or something, and you're doing some induction over like this, like the different gates you might see or something, you're just manipulating one by one. There's like no space for an oracle to fit in there. There's this kind of, I mean, you can define circuits with oracles in them, and you can study these things, and there are interesting results. But if your argument is like, induction based on 3 cases, and it only is working because like these are your 3 cases or something like that, then it's pretty clear that this is not going to relativize. But okay, so this is kind of why people were looking at starting to look at circuits instead of Turing machines, because it feels like you got to get down to the bit level of the operations. Do you think that requiring M to be efficient is a strong restriction to applicability of M? This is a very interesting question, because most people thought that this was the weakness in the Rasburov-Rudich barrier, but I have some theorems which we will see. I will not prove, but we will see the statement of which actually. Just to maybe give a little bit away, actually, it's this random Boolean function business that is the problem. But yeah, I'm gonna just leave it like that for now. But yeah, it turns out that this efficiently thing is not a serious problem. In fact, like you've got to have some method that will distinguish easy from some function to prove interesting lower bounds at all. There is a formal way of saying that, which we will see later. Yeah, it turns out that it's unexpected that this one is actually the first one is what's really doing the work here. Yeah, because I think this implementation of efficiently was what people believed. So the third group of non-relativizing methods, I'm just going to call faster simulation methods, and there's lumping several different things together. So there's the theorem of Paul, Pippinger, Simoretti, and Trotter that non-deterministic linear time for multi-tape Turing machines is different from deterministic time for multi-tape Turing machines. Okay, there is a series of theorems starting with Fortnell showing that this SAT problem cannot be solved by algorithms simultaneously using time into the 1.8 and space order log n. You can make this space bigger, but this 1.8 is kind of a sticking point right now. And there's another sequence of theorems that show non-uniform circuit lower bounds for classes for which lower bounds have been open for decades, mainly as far as we could tell because of this Rasburov-Rudich barrier. Okay, the common theme to these kinds of lower bounds is that they all have some algorithmic component where at a really high level, a problem based in the weak class, like a ACC circuit, whatever that is, it's just a weak kind of circuit, much weaker than what you might think would be interesting. So a problem based in the weak class, or like a time-space algorithm, or like just a deterministic multi-tape Turing machine, some problem based in that can be solved faster using the resources of the stronger class, like say MP or non-deterministic time or SAT or something like that. So just to give an example, this theorem was proved in the 80s by showing that time t on multi-tape Turing machines can be sped up. It can be solved in little o of t time if you give me non-determinism and you give me a SAT oracle. Okay, so this is like, you know, this is using some non-determinism and well also some co-non-determinism, some SAT queries. But this is the driving theorem behind this non-relativizing statement. And so like when you have this kind of like algorithm where you're analyzing the weak class and solving it faster using the strong one, I don't know of any kind of unifying barrier against these methods. Some of them have one-off barriers. Like there are reasons to think that we need radically new techniques to get this. There are reasons to think this. There maybe I don't know of a reason we couldn't get better lower bounds for this maybe, but like they're all kind of their own thing, and there's no unifying barrier known against these methods. And maybe the way to future lower bounds is algorithmic. I mean, this is certainly what I think, but yeah. So those are the three rough classes of methods: algebra methods, probabilistic methods, faster simulation methods, for lack of better terminology. So let me now discuss this algebraization barrier. Okay, so this was first proposed by Aronson and Vigderson and refined by Implazo, Kobinets, and Kolokolova. So this is a strengthening of relativization that applies to these algebra methods, so the class 1 methods. So let me just say at a high level what this is. I don't have the time or maybe even inclination to go too far in depth in it, but you basically say my simulator gets more power, more oracle power than my simulated, the thing I'm simulating. So like P-space with an oracle for A can be simulated with interactive proofs, but we get some new powered, high powered oracle A. And this A tilde means you can query not only the oracle A, but you can even query a low degree polynomial that agrees with this A on Boolean values, okay? But the point is, like the polynomial agrees with A on Boolean values, but you could query it, you know, over a larger field. You can query it on non-Boolean points, like a polynomial, right? So this is what you are allowed. So this IP thing gets to ask like weird types of questions the P-space machine doesn't. Okay, the simulator has more power than the simulator with respect to the oracle. And when you do this, when you allow this sort of extra power, you can get these containments. Okay, so in this sense, the P-space equals IP statement algebraizes. I mean, there are ways to kind of like, I mean, maybe it looks a little weird that like this one is less power than this one. There are ways to kind of clean that up, but this is like the original Aronson Vigderson version, and I think it's clear that that something extra is going on here whenever we throw in this extra oracle power. But you also get this for like this nx equals MIP thing. You get it for these circuit lower bounds I mentioned, but nevertheless, there are oracles so that like NP to the A is not NP even with this extra low degree. And you can simulate, which says my connection is unstable.
Ryan, I think we have missed the last minute or so of what you were saying. It seems that there was some problem with your connection.
Yeah, I can. It looks like my iPad thing has crashed a bit because it. Oh. Yeah.
Yeah.
Yeah, it just crashed for real then. Okay, hold on. I'll try it again. It's thinking about it. Maybe I'll stop and I'll try to share it again from scratch. Let's see. All right. All right. Looks like we're back. Looks like we're back.
Yeah.
Okay.
Yeah,
good.
seems so. Yeah.
Yeah. Yeah. Someone's asking. Sorry, I don't get what a wave is. Yeah. Maybe if you can hear what I'm saying, then you might get it this time. Okay. So yeah. Let me just say that like at a high level, what's going on is we get some extra field we can work over here, and the field is bigger than GF2. Okay. And the idea is that we can query not only A, but we can query the values of a low degree polynomial that agrees with A in Boolean values. So we can always take for any Boolean function, we can always get some multivariate polynomial that agrees with it on 0, 1 values. If we think of 0, 1 as being in like a field. Okay. The point here is that, yeah, we have a low degree. So in each variable has like some, like, let's say quadratic degree in this thing to give it a little bit more freedom. And then when you do this, so when you have this ability to like query a polynomial and get back the value of that polynomial, you can talk about querying it on non-Boolean points. Like what happens when I query it on like 2? Like I just give it all 2s instead of 0, 1 points. And when you do this, you get more power. I don't have time to kind of explain how you get more power. But let me just say that like there's a whole class of these methods like going on in P space equals IP where you get strictly more power. And so what's going on here is that we're saying something stronger than there is an oracle for which P is different from MP. We're saying that like MP, given the oracle A, still can't be simulated by P, even if I get to query this low degree polynomial that agrees with A. So I get to query it on strictly more points. I get to like do some weird things like query it on all 2s, the string, like the string of all 2s, but nevertheless, I still can't simulate MP, right? And in fact, there's oracles so that like if I have MP and I've got like this low degree polynomial I can query, I can actually simulate that in P to the B. This is by choosing like a very interesting oracle B, so that this happens. Let me just leave it like that. And there are oracles for which like non-intrinsic time 2 to the n, even with this like low degree polynomial can access, this can be simulated with linear size circuits. So a different circuit for each input length that just calls an A oracle, right? So like proving kind of like interesting circuit lower bounds and things like this are also going to require non-algebraizing techniques. So things that like somehow like don't hold up if I get to query low degree polynomials. Okay, so an interesting point is that this PCP theorem that I mentioned, it does not algebraize. And so it's some of this one-off, like the fact that you taking these constantly many queries is somehow important. Okay. Oh, good. So it looks like I'm ending right on time. Okay, because like I plan to do this for the first part, and then the Rasborov-Rudich barrier will be the second part. Wow, that was.
May I ask a question?
Fingers crossed for the next section. Okay. Yes.
Yeah, a question. So this querying this extended oracle, is it the right intuition that if I now extend my my oracle beyond the binary string, so it's on larger field, then sort of by querying as you say, on 2s or 3s, I can sort of get in one query some kind of an aggregate of the information about the initial polynomial, and therefore it gives me more power.
Absolutely.
Yeah.
Absolutely.
Okay,
Yeah. So if you're familiar with like the sum check protocol, like the interactive proof showing that SharpSat has interactive proofs. Essentially, yeah, you're using randomness to quickly verify that an exponential size sum equals a certain value
I see.
by polynomial interaction. Yeah. It is like if you set up the correct polynomial and you're thinking about it in the correct way, then querying it on these additional values, yeah, it gives you some kind of sum aggregate information. Yeah.
Okay, good. Yeah,
it's a good way to think about it. Yeah. There are other questions, I guess.
Yes.
We can just take a break. I mean,
right. So yeah, I did not catch. So essentially, we are done, like with the first part, right?
Yes.
Yes. Okay.
Yes.
Good. So
next part
any
will
questions?
Be on reservoir fruitage. Yes.
Yeah. Any other questions from the audience? Unmute yourselves if you would like to speak, or write in chat. Okay, doesn't seem so. So I think that we now take a break. Let's go back on schedule. I think it was 10 past 5 p.m. Warsaw time.
Yeah.
So in 17 minutes, according to my clock.
Okay.
Yeah. So grab a coffee, grab a tea, whatever you like, and we are back at this point.